On June 23, 2025, at precisely 5:30 in the afternoon Central European Time, an image appeared on screens at watch parties hosted by universities, planetariums, and research institutions across 6 continents simultaneously. It had been taken by the largest digital camera ever built, attached to an 8.4-meter telescope perched 2,182 meters above sea level on a mountain in the Chilean Andes called Cerro Pachón. The image showed 2 nebulae, the Trifid and the Lagoon, in a single frame so detailed that it required 400 4K high-definition television screens displayed side by side to show it at full resolution. The crowd at the Adler Planetarium in Chicago erupted. The scientists watching the live stream at institutions from Tokyo to Tucson fell quiet for a moment, then began talking all at once. And the observatory that had just released that image, the Vera C. Rubin Observatory, named after the pioneering American astronomer who discovered evidence for dark matter and spent her career fighting for recognition in a field that resisted her at every turn, had done something that no telescope in history had done before. It had opened its eye for the first time, and the universe it was looking at was going to spend the next 10 years giving up secrets it had kept for billions of years. Scientists described themselves as beyond excited about what was coming. That description turned out to be an understatement. To understand why Vera Rubin's first images stopped the world, you need to understand what the observatory was built to do, and why nothing like it has ever existed before. Most telescopes are designed to look at specific things. You point a telescope at a star, or a galaxy, or a nebula, and you study it. You spend hours or nights collecting light from that single target. The Hubble Space Telescope works this way. The James Webb Space Telescope works this way. Their extraordinary power comes from their ability to collect very faint light from very specific targets with very high resolution. They are deep but narrow. Vera Rubin is the opposite. It was designed not to stare deeply at one thing, but to scan broadly across everything. Its 8.4-meter mirror collects more light per unit time than almost any other ground-based telescope. Its 3,200 megapixel LSST camera, the largest digital camera ever built, roughly the size of a small car, roughly twice as heavy as a small car, assembled and managed at SLAC National Accelerator Laboratory in California, captures a patch of sky equivalent to 45 full moons in a single exposure of approximately 40 seconds. After each exposure, the telescope moves to the next patch, takes another 40-second exposure, and moves again. Every 3 to 4 nights, this process covers the entire visible southern sky. Every night it starts over, for 10 years. This is the Legacy Survey of Space and Time, or LSST, a 10-year time-lapse movie of the entire southern hemisphere sky, accumulated into a dataset of approximately 30 petabytes of astronomical images, processed in real time by a computing pipeline powerful enough to detect changes between images taken nights or weeks apart, and generating alerts about those changes that go out to astronomers worldwide within 60 seconds of the observations being made. The first images released on June 23, 2025 were not from the full science survey. They were from the commissioning phase, the period when the telescope and camera systems were being tested and calibrated before the full survey began. But even commissioning data from Vera Rubin is extraordinary. The Trifid and Lagoon nebula composite image was assembled from 678 individual exposures. It revealed structure in both nebulae, the clouds of gas and dust where stars are forming, at a resolution and depth that showed faint features invisible in previous imaging. Stars at the edges of the nebulae's illuminated regions, normally drowned out by the brighter central emission, were visible as individual points of light. The full image, when displayed at its native resolution, would cover an area of wall roughly the size of a tennis court. The second major image released that same day showed the Virgo Cluster, the enormous gravitational concentration of galaxies approximately 55 million light-years away that anchors the local supercluster of which our Milky Way is a peripheral member. The Rubin image of Virgo covered an area 2.4 times larger than the camera's standard field of view, assembled as a mosaic, and it contained approximately 10 million individual galaxies. 10 million galaxies in a single image. And that, as the caption accompanying the image noted, represented approximately 0.05% of the 20 billion galaxies that LSST will ultimately capture over its 10-year survey. If 10 million galaxies is 0.05% of the final catalog, the full Rubin universe, the complete dataset this observatory will eventually produce, will be the largest map of the cosmos ever assembled by any instrument in history. The first images also came with a discovery that nobody expected from commissioning data. As part of the first look event in June 2025, Rubin announced that it had observed thousands of asteroids in our solar system, approximately 119,900 of which had been confirmed as never before seen, 1,900 new asteroids found in 10 hours of test observations. The full science survey had not even begun yet. Within those 1,900 new asteroids, a team of astronomers identified 19 super and ultra-fast rotating asteroids, objects spinning so rapidly that the centrifugal force at their surfaces approaches or exceeds the gravitational force holding them together. And one of those ultra-fast rotators became the subject of the first peer-reviewed scientific paper ever published using Rubin data. The asteroid, designated 2025 MN45, is 710 meters in diameter, nearly the size of 8 football fields, and it completes a full rotation every 1.88 minutes, 1.88 minutes. For comparison, Earth rotates once every 24 hours. This asteroid completes a full rotation in less time than it takes to brush your teeth. It is the fastest ever spinning asteroid with a diameter over 500 meters that scientists have ever found. Its spin rate has direct implications for its internal structure. At that rotation speed, a rubble pile asteroid held together by gravity alone would fly apart. The fact that it has not means it must be a monolithic, solid object, a single coherent rock, rather than a loosely bound collection of debris. That distinction matters for planetary defense planning because the methods for deflecting a solid monolithic asteroid are different from those used to deflect a loosely bound rubble pile. The alert system that Vera Rubin was designed to operate, the mechanism by which every change detected between images taken on different nights, is instantly flagged, packaged, and broadcast to the global astronomical community, reached its first major milestone on February 24th, 2026. On that date, Rubin launched the Rubin Real-Time Discovery Alert System, which captured 800,000 transient alerts in just a single night. 800,000 alerts in one night. Each alert represented a detected change somewhere in the sky, a star that had brightened or dimmed, an object that had moved, a point of light that had appeared where none was before. These alerts called scientists' attention to new asteroids, exploding stars, and other changes in the night sky. The system is expected to eventually generate up to 7 million alerts per night when operating at full capacity across the complete survey area. 7 million changes in the sky, detected, characterized, and broadcast to astronomers worldwide, every single night. For comparison, the entire previous generation of sky survey systems, all of them combined, generated perhaps tens of thousands of alerts per night at their peak. Rubin increased that number by orders of magnitude on its first operational night. The alerts go out through a broker system that distributes them to subscribing institutions worldwide, where automated software pipelines trained on machine learning algorithms sort and classify them in real time, flagging the most scientifically interesting events for immediate human follow-up. When a supernova explodes in a galaxy 500 million light-years away, Rubin will detect the brightening within hours of the explosion's light reaching Earth, and astronomers worldwide will have an alert within 60 seconds, giving them time to point other telescopes from the very large. Telescope in Chile to the Keck Observatory in Hawaii to the JWST in space. At the event, while it is still evolving. The LSST officially began on July 1st, 2026, with NSF Acting Director Brian Stone announcing, "Today, we begin filming the greatest cosmic movie ever made." The delay from the originally anticipated early 2026 start was acknowledged openly. LSST head Jelko Ivezic explained that the decision to officially begin was made after a period of systems optimization and a careful operational review of technical readiness, data system performance, and scientific validation. The months between February 2026 and July 2026 were spent in what the team called the operations rehearsal phase, running the full system, from telescope pointing to data processing to alert generation, as if the formal survey had begun in order to identify and fix any remaining issues before the 10-year clock officially started. By July 1st, the system had been validated to the team's satisfaction, and the greatest cosmic movie in history began. Before the full survey started, Rubin's early optimization data had already produced a solar system discovery of extraordinary scale. Using preliminary data gathered during early optimization surveys, spanning a month and a half, scientists discovered 11,000 new asteroids in the solar system, confirmed by the International Astronomical Union's Minor Planet Center. This constituted the largest single batch of asteroid discoveries in the past year. The dataset that produced those 11,000 new asteroids involved 1 million individual observations. 1 million observations in a month and a half, yielding 11,000 previously unknown objects in our own solar system. And embedded within that dataset were approximately 380 trans-Neptunian objects, the icy bodies that drift in the cold outer reaches of the solar system beyond Neptune's orbit, in the realm where comets originate. 2 of the newly discovered trans-Neptunian objects, provisionally named 2025 LS2 and 2025 MX3Q48, have extremely large, elongated orbits. At their farthest point from the Sun, they are roughly 1,000 times farther away from the Sun than Earth. Objects with orbits that stretch to 1,000 astronomical units are in the territory where theorists have long predicted that Planet 9, a hypothetical undiscovered planet roughly the mass of Neptune, might exist and might be gravitationally influencing the orbits of distant trans-Neptunian objects. Whether the elongated orbits of 2025 LS2 and 2025 MX348 are consistent with Planet 9's predicted influence is something that researchers are actively investigating. Rubin was not designed primarily to find Planet 9, but it may be the instrument that finally settles the question of whether it exists. The science goals that motivated the construction of Vera Rubin Observatory were formally organized around 4 primary themes. The first is solar system science, the complete inventory of moving objects in our solar system, from near-Earth asteroids that could pose a threat to Earth, to the main belt between Mars and Jupiter, to the trans-Neptunian population, to the long-period comets from the Oort cloud. The current catalog of known solar system objects numbers in the hundreds of thousands. Rubin is expected to increase that catalog to several million objects over the survey's 10-year duration, discovering most of the remaining undiscovered near-Earth asteroids above 140 meters in size, the size threshold above which an impactor could cause regional to continental devastation. The Planetary Defense Coordination Office at NASA has designated the discovery of undiscovered potentially hazardous asteroids as one of Rubin's highest priority contributions to national security. Every new near-Earth asteroid that Rubin discovers and characterizes is an object that emergency planners can add to their models, improving the estimate of how much warning humanity would have before a potential impact, and whether deflection would be feasible. The second major science theme is the transient universe, events that change on timescales of minutes to years, including supernovae, gamma-ray bursts, gravitational wave optical counterparts, variable stars, active galactic nuclei, tidal disruption events where a black hole shreds a star, and the optical afterglows of fast radio bursts. Each one of these event types is scientifically significant in its own right, but the critical requirement for studying them is catching them early, ideally within hours of an event beginning, when the most physically informative emission is happening. Current sky surveys catch many of these events, but they catch them late, and they sample the sky too infrequently to catch the fastest. Evolving phenomena. Rubin's combination of wide coverage and rapid cadence, returning to each part of the sky every 3 to 4 nights, with some fields visited multiple times per night, gives it a uniquely powerful transient detection capability. The 800,000 alerts generated on the first night of the alert system test in February 2026 included flagged candidates for hundreds of supernovae in various stages of their evolution, dozens of active galactic nuclei showing brightness changes, and multiple fast-moving solar system objects identified within hours of their detection. The 7 million alerts per night that the full LSST will eventually generate will include supernovae detected within hours of first light, gravitational wave counterparts identified within minutes of LIGO alerts, and potentially new classes of transient events that current surveys do not detect because they evolve too quickly between sky visits. The third major science theme is the Milky Way, the mapping of our own galaxy at a depth and completeness that will allow astronomers to reconstruct its formation history. Rubin will detect individual stars in the Milky Way and its satellite dwarf galaxies down to extremely faint magnitudes, building a 3-dimensional map of stellar populations across the galaxy's disk, halo, and bulge. From the distribution and chemistry of those stars, encoded in the infrared colors and brightness variations that Rubin will measure over 10 years, astronomers can trace the merger history of the Milky Way, identifying the stellar streams left behind by ancient dwarf galaxies that were absorbed billions of years ago, and reading the chemical evolution of the galaxy across its history. This galactic archaeology program is impossible at the depth Rubin will achieve with any existing sky survey. The density of stars in the Milky Way's disk is so high that previous surveys could not go deep enough to see the full extent of the stellar halo, where the oldest and most chemically primitive stars, the fossil record of the galaxy's earliest history, are found. Rubin will reach those stars, and the dataset it builds of stellar positions, motions, and brightness variations over 10 years will feed a generation of research in galactic archaeology and stellar population modeling. The fourth and ultimately most consequential science theme is cosmology, the structure of the universe on the largest scales, and the nature of the dark matter and dark energy that dominate its composition. Dark matter, which makes up approximately 27% of the universe's total mass energy, is detectable only through its gravitational effects. When light from distant galaxies passes through the gravitational field of intervening dark matter concentrations, the images of those background galaxies are subtly distorted, a phenomenon called weak gravitational lensing, by measuring the shapes of hundreds of millions of galaxies across enormous areas of sky and looking for the coherent patterns in those shape distortions that indicate the presence of dark matter. Rubin can build the most detailed map of dark matter's distribution across the Observable Universe Ever Assembled. That map directly probes the properties of dark matter, its mass, its clustering behavior, its relationship to the luminous matter it gravitationally shepherds, and constrains the models that attempt to explain what it is: dark energy, the mysterious component making up 68% of the universe's total. Energy content and driving the accelerating expansion of the universe manifests in how the large-scale structure of galaxy clusters and cosmic filaments evolved over time. Rubin's deep imaging of billions of galaxies across cosmic time, combined with precise measurements of their distances through photometric redshift techniques, will build the most powerful dataset ever assembled for measuring how cosmic structure grew, and therefore for constraining how dark energy behaved throughout the history of the universe. The Hubble tension, the disagreement between different methods of measuring the universe's expansion rate, may find its resolution in the Rubin dataset, which will measure weak lensing across a cosmic volume large enough to independently determine the expansion rate at multiple epochs. Brian Stone, performing the duties of the NSF director, stated that Rubin Observatory will capture more information about our universe than all optical telescopes throughout history combined. That statement is not hyperbole. Over 10 years, LSST will produce 30 petabytes of raw image data, a volume that exceeds the combined data output of every optical telescope ever operated, summed across the entire history of astronomy from Galileo's first telescope in 1609 through the night before. Rubin began its survey in 2025. The 20 billion galaxies that will eventually populate Rubin's source catalog represent a substantial fraction of all galaxies in the observable universe, bright enough to be detected by any ground-based telescope. The catalog of solar system objects will be the most complete inventory of our cosmic neighborhood ever assembled. The transient alert stream will drive follow-up campaigns that span the entire global network of professional observatories, with Rubin's detections acting as the trigger for hundreds of coordinated observational responses every night. The Milky Way map will resolve individual stars across distances that current instruments cannot reach, revealing the full three-dimensional structure of our galaxy for the first time. And the cosmological dataset, the billions of galaxy shapes, redshifts, and positions that will constrain the nature of dark matter and dark energy, will be the foundation of observational cosmology for the decades that follows the survey's completion. Vera Rubin herself spent her career proving that something unseen was holding galaxies together, that the visible matter in spiral galaxies could not account for the speed at which their outer edges were rotating, and that an invisible component, dark matter, was the missing piece. She spent decades making observations that other astronomers initially dismissed, working in an era when women were excluded from major observatories, fighting for telescope time that the establishment was reluctant to grant her. She died in December 2016, 3 years before the ground was even broken for the observatory that bears her name. She never saw the instrument that will spend the next decade mapping the invisible matter she spent her life proving exists. The first image from Vera Rubin Observatory, shown on screens around the world on June 23, 2025, contained 10 million galaxies. Each one of those galaxies is embedded in a halo of dark matter. And over the 10 years that follow, the telescope built in her honor will map those halos across the universe with a completeness and precision that she could not have imagined from the telescopes available during her lifetime. The greatest cosmic movie ever made began on July 1st, 2026. It will run for 10 years. And what it reveals about the universe, about where we come from, what the cosmos is made of, and how it all began, will define the next chapter of humanity's understanding of existence. The watch parties held around the world on June 23, 2025, from Chicago to Tokyo, from Sao Paulo to Edinburgh, were not merely celebrations of a telescope coming online. They were the global scientific community acknowledging that a new era had begun. The Hubble Space Telescope changed astronomy by seeing deep. The James Webb Space Telescope changed it again by seeing farther and in wavelengths that revealed what was hidden. Vera Rubin changes it in a third way, by seeing everything, continuously in motion, in time. The universe is not a static photograph. It is a dynamic, ever-changing system in which stars explode, asteroids move, black holes flare, galaxies collide, and gravitational waves ripple through the fabric of space. For most of the history of astronomy, our view of that dynamic universe was limited by the difficulty of watching large areas of sky often enough to catch events as they happened. Vera Rubin eliminates that limitation. It watches the entire southern sky every 3 to 4 nights, without exception, for a decade, building not just an image, but a history, a record of how the universe changed event by event across 10 years of continuous observation. The first images stopped the world. The next 10 years of data will change it.